Hello, this is the fifth complex numbers video of the OCR Pure Core AS Further Maths, and the title is Terminology. This session also considers an alternative way to conduct division of complex numbers. In previous sessions, we introduced the notation of using the Z to represent a complex number equal to A plus BI, where A and B are real, and I is the square root of -1. An alternative way of saying A and B are real are to write that A and B are in R. We've also discussed the fact that a complex number has two parts. A real part, sometimes written with this notation, RE or real of Z is A, where A is also real, and an imaginary part, sometimes written as IM or imaginary part of Z equals B, where that coefficient B is also real. In looking at the solutions to quadratic equations, and in the previous session on complex number division, we also talked about the idea of a complex conjugate. Here you can see that this is generally denoted by Z star, where of course Z star then equals A minus BI. A and B are still real and are the same values as they were for Z. Also in the previous session, we looked at the complex conjugate product, here written as Z star, which again will always be real and equal to A squared plus B squared. When we covered the addition and subtraction of complex numbers, we discussed this idea of gathering like terms, just as we did in algebra. Sometimes we may want to consider the equality of complex numbers and solve problems using their real or imaginary elements or terms. Let us consider the equation where A plus BI is given as 7 minus 4i. In other words, A is 7 and B is -4. The equality implies the real parts must be the same. That is how I'm able to say, well, A must be 7. Equality also implies that the imaginary parts must be the same. Therefore, I was able to state, well, B must be -4. It's worth noting that complex numbers are only equal if the real terms and the imaginary terms are each equal. Here we have an alternative approach to division, where we can set two complex numbers, Z divided by W, equal to some other complex number, A plus BI. In the example here, Z equals 3 minus 2i and W equals 3 plus I. Given that 5 plus I is not equal to 0, we can then multiply both sides of this equation by that denominator, remembering when we multiply out, of course, that I squared equals -1, and then by rearranging and collecting the terms. So here we have that 3 minus 2i equals A plus BI multiplied by 5 plus I, which would give us 5A plus 5BI plus AI plus, and again I'll keep the I squared in for the moment. Gathering the real terms, that would give us 5A plus, minus B for the real part, and then A plus 5B for the imaginary part. Remembering then that the real parts must equate and the imaginary parts must also equate for that equation to hold, we have, looking at the real, that 3 must equal 5A minus B, and then the imaginary, that -2 must equal A plus 5B, thus giving us two simultaneous equations in the two unknowns. We can solve these simultaneously to give us A equals 1/2 or b equals minus a half. I don't know which type of simultaneous equation solutions you like to use, but you can use either substitution or elimination to do this. Equating parts can also be used to solve other types of problems. Here we are given that z equals x plus yi, and we need to find the value of x and y such that z plus 3iz conjugate equals minus 1 plus 13i. And they tell you or remind you that z star is the conjugate of z. So let's just first of all write down that conjugate. We know it's going to be x minus yi. Then just doing, perhaps first, we'll just work out what 3i z conjugate will be before we start adding those. And you can see that that's going to be 3xi, just to put the I at the end, and then that we've got, let me write it as minus 3yi squared, but then we do know that that of course is then going to be plus 3y because the minus I squared will be plus 1. So then going back over here, z plus 3i conjugate of z, or z star, is going to be x plus yi plus this 3y plus 3xi. Gathering our real parts, that gives us x plus 3y. And then we have the 3x plus y, the imaginary part. Now, we've been told that that equals minus 1 plus 13i. And again, using this idea that the real parts must be the same, we can then say that minus 1 equals x plus 3y. And the imaginary, that we have 13, that coefficient 13, is going to be the same as 3x plus y. And once again, we can solve that by simultaneous equations. I think I'll do it by elimination in this example, I think. So I'm going to say that I'm going to multiply that 1 by 3 and say that's 3x plus 9y equals minus 3. And then that one's going to be just 3x plus y equals 13. That will give me 8y equals minus 16, or y equals minus 2. And then if I substitute back in, I would end up with 8 minus 6 equals minus 1, or x equals 5. And then I would probably state very clearly somewhere, well, I know that I've got these results, x equals 5 and y equals minus 2. Sorry, sometimes my 2's and my z's do look rather similar. And here we have the summary slide for that calculation. In the next session, 1.6, we will link complex roots to quadratic